Hi, I'm Leah from Queensland University of Technology, and this talk is part of a mini-symposium on Stein's method in computational statistics at MCQMC 2020. I'll be talking about a couple of papers today in the field of Monte Carlo variance reduction using Stein operators, and another talk in this session by FX Briol will be about speeding up computation in these types of estimators. So I'm a collaborator with Chris Oates on both of these papers, and also with several other people mentioned here on the two different papers. Okay, so for the setting for this work is that we have a set of n samples from some distribution pi, and we also have the associated gradients of log pi. So this is the setting, for example, if you've done MCMC using a gradient-based sampler. So we've got these samples and gradients, and we want to evaluate some expectation of a function f of interest. Typically, we just go straight to using vanilla Monte Carlo estimation. So we evaluate f for each of our samples, and we take the mean. If our samples were actually independently and identically distributed according to pi, then we'd have an unbiased estimator for our expectation of interest, and the error for this estimator would be of the order 1 on root m. So if we wanted to reduce the standard deviation of this estimator by a factor of 10, we need 100 times as many samples. And getting samples is an expensive way to reduce the variance of an estimator when you consider that each sample requires typically a likelihood evaluation and a function evaluation. So this talk proposes two novel estimators which improve upon vanilla Monte Carlo integration when you've got your samples and your associated gradients of the log target. And all of the methods I'll be talking about today are available in the R package ZVCV that we've developed. Okay, so the methods I'll be talking about are types of control variates. So just to set up notation for that, what we've got in black is our vanilla Monte Carlo integration estimate, and in red is the stuff we add for control variates. So instead of evaluating f at each of our samples, we evaluate f minus f tilde, and then to account for that we add back on the true expectation of f tilde, which of course requires that that's something we can evaluate. The intuition behind this, if we've actually got independently and identically distributed samples, is that we've still got an unbiased estimator for our expectation, but we get a reduced variance estimator. And the key to that is this term here. So essentially, if we can get an f tilde that looks very close to f, then we could end up getting an estimator that's very close to the true value consistently. So it could be even to the case of being perfect. So the things that we look for in a control variate is the ability to evaluate the true expectation of f tilde under pi, the ability to compute f tilde at each of our samples easily, and of course the main thing we want to do is to get reduced variance. So we want the variance of f minus f tilde to be much less than the variance of f. And that variance could be, for example, the variance under the law of the Markov chain if you're getting your samples from MCMC. And it turns out actually that there are some control variates that are available in general when you've got your samples and your gradients of the log target. And those control variates are based on Langevin Stein operators. So Chris Oates and others were the first ones to realize this general framework for developing control variates based on the gradients of the log target. So what they do is they choose their function f tilde to be a constant plus this Stein operator applied to a function g, which you have the freedom to choose. I'm using the term Stein operator to refer to operators that result in zero expectation under pi, but actually Stein normally refers to the ability to track convergence and non-convergence. So here I'm just talking about zero expectation properties. There's a few different types of Stein operators, but we're looking specifically at the Langevin Stein operator. So the format for that is we get the gradients of the log target, and then we also get some first and second order gradients of our function g of interest. So all we need to be able to evaluate our control variate is the gradients of the log target, some samples, and a user-specified function g with its gradients. It's easy to show that we get zero expectation under some regularity conditions. I won't go into those in detail, but if you're interested, here's some details. And then to actually compute the estimator, I just wanted to simplify that down a bit for you. So the top line is our control variate formula. Then we're plugging in our formula for f tilde and the fact that its expectation, the expectation of the Stein operator applied to g is 0. And down here we get that our estimator has this form here. So that's something that's quite easy to evaluate. So now we know we've got a zero expectation or known expectation. We can evaluate our control variate. So what's remaining is to choose our function g so that we get reduced variance estimators. And the key is to select g from some general class functions by optimizing some criterion. Okay, so the competitors that exist are about how to choose your general class of functions g. The first one is choosing g to be a qth order polynomial. So this is relatively simple to implement, and this came from Asaraf and Caffarel in 1999 in the physics literature, and Antonio Tamira and others brought that into the Monte Carlo and statistics literature with some theory. So what we have is that our function g is just some polynomial, and a polynomial can be written as a weighted sum of monomial terms. So that's what we've got here. The Stein operator is just a linear differential operator, so that's how we get to this line. And finally we end up that our function f tilde is a constant plus some coefficients times by x, where x is just a vector of terms involving theta and the gradients of the log target. So you might look at this and notice this actually looks a lot like linear regression. That's essentially what we're doing. We want f tilde to be as close to f as possible, so we want to do something that looks like a regression of f on a plus beta x. So this is very easy to implement in practice. The current approach is to estimate a and beta using ordinary least squares. So that's just, a normal linear regression approach. You might want to consider an alternative based on minimizing the variance of the asymptotic variance of the Markov chain, but we don't look at that here. That's done by some other authors. Essentially, the resulting estimator just looks like this. Okay, and the other approach that's really popular is from Chris Oakes' 2017 paper on a method called control functionals. So what they do is, instead of choosing g to be a polynomial, they choose g to be from a reproducing kernel Hilbert space. So the formula for how you do the optimization looks similar in some ways, but g here is from an RKHS, and there's a regularisation term here on the end, so you can think of this as regularised least squares. In practice, when you want to perform control functionals, what you do is you choose some kernel, for example a Gaussian or a term, and that will have some length scale parameter. And then you estimate that parameter using something like cross-validation. And finally, once you've got that, you do solve the n by n linear system and you end up with a solution like this. So K0 is just the matrix of the Stein operator applied to our kernel, evaluated at each of our sample combinations. And so we've got to do the inverse of an n by n linear system and a few matrix vector operations. So it turns out that this has order n cubed complexity. You can think of this estimator as the posterior mean with a Gaussian process prior with covariance K0. Okay, there's another approach also based on neural networks, but that's much more recent and it's a bit less popular at this stage, so I'm not going to go into that. Just in terms of benefits and disadvantages of the two approaches, control functionals is order n cubed, so it becomes expensive as you have more samples. Zero variance control variates is of order j cubed plus mj squared, so it's linear in the number of samples, but it's cubic in the dimension and the polynomial order. Control functionals have some really nice properties saying that you can actually get better than 1 on root n convergence, and the amount that you get better depends on how smooth pi is and how smooth f is, as well as on the dimension. Zero-variance control variance doesn't have that property just for a fixed polynomial order, but it does actually give you the possibility to get zero-variance estimators. So if you've got a Gaussian target distribution pi, and you want to evaluate the expectation of some polynomial, then ZVCV will give you the exact answer. So you get zero-variance estimators in ZVCV in that setting. Some empirical results suggest that ZVCV may outperform control functionals in higher dimensions as well. Both of these methods are based on all of your gradients being available, which may not always be the case if you can't store them, or if you've got a model based on an ODE that can become harder to solve to get some of the gradients. And these methods are typically only applied in very small dimensional settings, for example, dimension less than or equal to 4. So the contributions of this work are based on 2 papers and a comment. So regularized ZVCV is our first paper, which improves the flexibility of ZVCV. It gets better performance for higher dimensions, and we develop some methods for when you only have a subset of your derivatives. Semi-exact control functionals balances the potential exactness of ZVCV with the improved convergence rates of control functionals, and the unbiased MC-MC approach, which I don't have time to talk about today, is essentially just applying these types of methods in the unbiased MC-MC setting, where you need to be a bit more careful about how to do your optimization to choose G. Okay, so the first paper, regularized ZVCV, the first thing we looked at is, can we get better performance by increasing the polynomial order? And there's a couple of ways to motivate that. One is that there's a paper saying you can get better than 1 on root n convergence when the number of control variates grows with the number of samples. So potentially we could increase the polynomial order as the number of samples increases. There's also a theorem that says polynomial functions can be used to approximate continuous functions on closed intervals. So that's another reason that increasing the flexibility of these polynomial approaches may be a good idea. The problem, of course, with that is that if you increase the polynomial order, you get a lot more terms in your regression. And we know that that uses more degrees of freedom, and it may result in overfitting. So the 2 approaches that we look at to overcome this are ridge regression, which is an L2 penalization, and LASSO, which is an L1 penalization. We also look at an alternative approach based on prior information and using that to overcome the curse of dimensionality. So to give a little bit of detail about ridge regression, what you can see in black is just the same as what we had for standard ZVCV, except we've standardized our response and predictors. And then on the right-hand side in red, you can see that we've just added on a squared, the squared L2 norm of beta times lambda. So it turns out that you can actually interpret this approach to ZVCV as a computationally efficient version of control functionals with this specific kernel that's mentioned here. So we now have actually a linear cost in the number of samples rather than cubic. If you're familiar with the literature on regression, you'll know that L1 penalization can outperform L2 penalization. And that's specifically in the case when the response can be approximated by a sparse linear combination of predictors. And in our case, that's definitely something that could be true. So we look at LASSO. So just adding an L1 penalty on instead of squared L2. The third approach we call a priori regularisation. The idea is that typically we're going to build our polynomial, or in general our function g, based on all of our d dimensions or variables. But actually, perhaps we could get reasonable performance by only using a subset of our dimensions. One of the reasons you might do this is because you can write the Stein operator in this form here, and you'll notice that the gradients of the log target only appear in a dot product with the gradients of g. So if you build your g only on a subset of the dimensions, then you don't need the remaining dimensions gradients of the log target with respect to that. So you might want to choose the subset based on prior knowledge, for example, on whether the gradients of the log target with respect to that will be helpful in predicting your function f, or you might do it out of necessity because you can't store or actually evaluate those gradients. In general, that's going to lead to a loss of information, but there's one setting where it won't, and that helps you get some intuition on how to actually perform this method. So that setting is that your function is only a function of your subset, a subset of your dimensions. So for example, you're interested in the marginal posterior means, which are only a function of one of your dimensions, and then also that your the subset that you're using is independent of the remaining variables according to pi. And obviously this one's a lot more restrictive, because if that was true, you could just separate out your problem into multiple dimensions. So the first simulation study is looking at how a regularized ZVCV goes on some SMC or sequential Monte Carlo examples. Efficiency is defined for this example and the next in terms of how many times better the mean squared error is for the estimator in question compared to vanilla Monte Carlo. So if you get an efficiency of 10, it means the mean squared error is 10 times lower, and that's without actually obtaining any additional samples. And n here is the SMC population size, or the number of samples you have. So firstly, we look at estimating posterior expectations. I'm not going to go into too much detail about this plot, but the darker blue colours are the higher order polynomials. So you can see in general, if you have a high enough number of samples, the higher polynomial orders go better. So the solid lines are just for ordinary least squares or cross-validation. The dashed lines are for LASSO, and the dotted lines are for ridge regression. So in this case, you can see that we can actually get improved performance by using a higher order polynomial with LASSO than we could using ridge regression or using standard ZVCV. And in this particular example, efficiency was roughly 10 using a priori ZVCV. So there was a version of this approach that only used a subset of the dimensions, specifically a single dimension, and we got massive improvements still in terms of mean squared error. This is just looking at a different function of interest that's related to the evidence estimates, or the estimates of the normalizing constant. And in this case, you can still see the general trends that higher order polynomials with LASSO do perform well. But I'm sorry, I forgot to mention that red is control functionals and black is one of our cross-validation methods that we've developed. So you can see that our methods for cross-validation and our higher order polynomials with LASSO are quite competitive. Okay, and then just looking at a second example, which is 61-dimensional. That's much larger than you typically use for ZVCV or any of these approaches actually. And you can see that in this particular setting, you can get some really big advantages by using a priori ZVCV. So really big meaning 2 times reduction in mean squared error, which is considerable when you're looking at only having 50 samples. The improvements we got on the other examples were more like 1,000 or more. And higher order polynomials go better with a higher number of samples. Okay, so that was regularized ZVCV. The second part of this talk, the paper is called semi-exact control functionals, or the method is called that, sorry. And the idea behind that is we want to balance the performance of ZVCV with the performance of control functionals. So we know that ZVCV can be exact in those Gaussian targets and polynomial function settings, and control functionals has improved convergence rates. So can we find a balance between these two? Okay, and the ideas come from the numerical integration literature. So in numerical integration, methods are based on estimating a function using either a minimum normal interpolant or by enforcing exactness on a pre-specified set of functions f, or curly f. Sard's method does both of those things by enforcing exactness on some pre-specified functions and then using the remaining degrees of freedom to find a minimum norm interpolant. So the problem with Sard's method and many numerical integration approaches is that it isn't typically feasible for Bayesian inference because there's an unknown normalizing constant, and integrals of the pre-specified functions and reproducing kernels with respect to pi need to be evaluated. It turns out that applying a Stein operator, which gives us zero expectation, removes these issues. So our new interpolant takes this form here. So you'll notice that this part here looks quite a bit like ZVCV if you choose your parametric basis to be a polynomial. And this part here looks a little bit like control functionals. So combining these two together gives us the benefits of both approaches. So we needed to develop a way to choose our coefficients B and A. And so we've done that to enforce exactness on our pre-specified functions and to do interpolation on each, so that f tilde is equal to f on each of our samples. So you can think of this like control functionals as using a Gaussian process prior, where our prior mean is informed based on our ZVCV approach. So actually estimating A and B amounts to solving this linear system here, and I'll refer you to the paper for more details, but essentially this is just this phi function, this phi matrix is just the Stein operator applied to our parametric basis, and K0 is the Stein operator applied to our kernels. So for what the estimator looks like, this top line is just the formula for control variates. We've done interpolation, so this part here is cancels out, and we know that the true integral of f tilde is just the intercept beta naught, or b naught, sorry. And so we get that the final estimator is of this form here, and this has computational complexity n cubed plus j cubed, where j is the number of terms in the parametric basis. So this is quite expensive, and so we developed some methods to reduce the cost of performing this. Specifically, we consider a Nyström approximation, and I don't have time to go into details, but for some number of samples, which is less than so for some n0, which is less than the number of samples, we have this linear system here. I've highlighted in red the parts that are different, but our K0 matrix is now a subset of our previous K0. Then we're going to use conjugate gradient to approximate the solution of this system, and we get a complexity which is now reduced, and it's no longer cubic in the number of samples. We have a couple of theoretical results in the paper. So the first is saying that, like ZVCV, if we choose a qth order polynomial basis, then our estimator is exact on all qth order polynomials for Gaussian targets, or in general in the Bernstein-von-Mises limit. We're also in the process of adding the consistency result, which is to say that our estimator goes to the true value in probability as the number of samples goes to infinity. And that's under certain conditions, and this is true even in the bias sampling setting where the Markov chain isn't actually pi invariant. So for the simulation study, we considered this kernel here, which is rational quadratic, I think, from memory. We use the same measure of statistical efficiency. And I'm sorry, this part here is from a previous talk, so that's not relevant at the moment. So I'm just going to go through one example just quickly, and this is a Gaussian example where we've got a very challenging integram that's got some polynomial terms, some sine terms, and exponential. So we can't actually evaluate this exactly because it's of the challenging integrand, but we can investigate the effective dimension and the number of samples. So on the left-hand side, you can see the efficiency as the number of samples increases, and I think this is for 4 dimensions. On the right-hand side, you can see the efficiency as the dimension increases, and I think that's for 1,000 samples. The orange color is our approach. Green is zero-variance control variates. Yellow is the cross-validation approach to select the control variates from the previous section of the talk, and blue is control functionals. So you can see that we get better performance than the alternatives as the number of samples increases. And of course, the performance deteriorates with dimension, but it still does go better than alternatives for quite a few number of samples. And you'll notice that control functionals with this particular kernel goes quite poorly in high dimensions. In general, what we found is that if control functionals went well on the problem of interest, then semi-exact control functionals can go similarly or better. And if zero-variance control variates went well, then semi-exact control functionals could go similarly or better. So regardless of whether the parametric or non-parametric approaches were working previously, our approach can be competitive with previous methods given a sufficient sample size. We also find that semi-exact control functionals has less sensitivity than control functionals to the kernel and its tuning parameters. We look at an explicit error bound, which I don't have time to go into, but you can see the paper if you're interested. So just to summarize, we had a paper called Regularized Zero-Variance Control Variates, where we improved the performance in higher dimensions. We looked at the possibility of using only a subset of derivatives, and we performed automatic control variate selection, which I didn't have time to go into, unfortunately. Semi-exact control functionals has the benefits of exactness of ZVCV and improved convergence like control functionals. And we also had a couple of theoretical results in that setting. The package ZVCV has all of the methods I've spoken about, and it's available on CRAN. And the limitations of these methods are that the performance depends on the choice of your function g. So there might be other approaches that you could look at besides choosing from a reproducing kernel Hilbert space or from a polynomial that might go well. Increasing the polynomial order to go to infinity as the number of samples goes to infinity isn't actually something that's feasible to do in practice when you get very large sample sizes, because it's computationally expensive to perform. Semi-exact control functionals is computationally expensive, although see FX's talk coming up in this session on ways to speed that up. And cross-validation to choose the best polynomial order approach is also computationally intensive. So in future work, we'd like to consider different parametric bases for semi-exact control functionals beyond just using a polynomial basis. We'd like to look at alternative regression methods like partial least squares or active subspaces. The parameterization that you choose affects the results. So if you're doing sampling on the log space, then you can take into account that transformation, and it might go better than doing your control variates on the original space. But it's an open problem how to choose that. And finally, there might be some cheaper alternatives to cross-validation for the ZVCV setting. Okay, thank you for listening.